Welcome dear viewers. We are continuing the discussion on transition and inner transition elements. In this module, we are discussing chemistry of organometallic compounds of D and F block elements. That is, we are focusing on the organometallic compounds belongs to transition and inner transition series. What are organometallic compounds? Organometallic compounds are those compounds in which the metal atom directly bonded to carbon atom. Organometallic compound denote the compounds that contain at least one metal carbon bond. Metal carbonyls, cyanides as well as carbides are also included in the category of organometallic compounds. Organometallic compounds can be classified based on nature of metal carbon bond present in them. There are three important categories of organometallic compounds, that is ionic bonded organometallics, covalently bonded organometallics, multicenter bonded organometallics. Let us enter into the details of each category. First of all, ionic bonded organometallics. These are organometallic compounds of alkali metals or alkaline earth metals, lanthanides as well as actinides. They preferably form ionic compound between metal and carbon. They are predominantly ionic. They generally colorless and extremely reactive. That means ionic bonded organometallic compounds are highly reactive. And most of such ionic bonded organometallic compounds are non-volatile solids and they are insoluble in organic solvents. Organic solvents are less polar and ionic bonded organometallic compounds are highly polar. As a result of the polarity difference, the solubility in organic solvent is minimum. Several examples of ionic bonded organometallic compounds are there. For instance, PH3 C minus Na plus, CS plus methyl minus, Na plus Cp minus. Cp stands for cyclopentadienyl anion or C5H5 minus. Now, the second category, covalent bonded or covalently bonded organometallics. Here, the covalent bond is the bond that exists between metal and carbon. That is the force of attraction connecting metal and carbon is covalent in nature. That covalently bonded organometallic compounds can be further divided into two important categories. They are sigma bonded organometallic compounds and pi bonded organometallic compounds. Now we can enter into details of sigma as well as pi bonded organometallic compounds. First of all, sigma bonded organometallic compounds. These are the organometallic compounds in which carbon atom of the organic ligand is bonded to metal by a sigma bond or a covalent bond. They are generally formed by most of the elements with the value of electronegativity higher than 1. That is, metals having electronegativity higher than 1 form this kind of sigma bonded organometallic compounds. For example, nickel tetracarbonyl NiCO 4 times, FeCO 5 times or iron pentacarbonyl. Another category of covalently bonded organometallics, that is pi bonded organometallic compounds. Here, the covalent interaction between metal and the carbon atom happens through pi bond or pi bond interaction exists between the metal and carbon atom of the organometallic compound. There are several examples. The two common examples are ferrocin, that is Cp5 twice Fe, and sea salt, that is KPtCl3C2S4. Multicenter bonded organometallic compounds are the last category. Here, in these compounds, there is a loosely bonded electron species exists with the coordination of metals like lithium, beryllium, aluminum, etc. That is, organometallic compounds of lithium, aluminum or beryllium preferably form multi-bonded organometallics. And examples include methyl lithium, Al2Me6, that is hexamethyl aluminium. Now we are entering into various ligands that are capable of forming organometallic compounds with metal. That is, in an organometallic compound, there must be two fragments. One carbon containing ligand that is capable of forming bond with the metal, and the second one is the central metal. And central metal may be D block element or F block element or even any main group metal. And in this case, we are focusing on various kind of ligands from which carbon atom is bonded to the organometallic metal. Here, these are some common ligands: carbonyl group, carbene or alkylidine, carbine or alkylidine, cyclopropenyl group, cyclobutadiene, cyclopentadiene or CP group. There are so many ligands, organic ligands, that are capable of forming organometallic compounds with a variety of metals. And ligands will continue in this chart also. Even benzene can form organometallic compound. A very popular organometallic compound that is formed by benzene is dibenzene chromium. That is a sandwich compound. We can later discuss on its structure. Now, classification of organic ligands based on hapticity. The term hapticity is highly important in organometallic chemistry, preferably whenever we are dealing with that organic ligands. So, in the case of organic ligands, the number of carbon atom that form bond with the central metal is termed as hapticity, or simply hapticity is defined as number of carbon atoms within bonding distance from the central metal atom. It denotes number of carbon atoms through which organic ligand is attached to the central metal. It is denoted by the Greek letter eta, that is hapticity eta. Ligands can be further divided based on hapticity. For instance, those ligands which can form bond through one carbon atom is denoted as monohaptoligand or eta one ligand. Methyl group is an example. Dihaptoligand, they can bond through two carbon atom. Ethylene molecule is a nice example for dihaptoligand. Trihaptoligand is provided from allyl radical. Tetrahaptoligand is nice example is butadiene. Pentahaptoligand, hexahaptoligand, etc. are there. Now we can arrange various organic ligands on the basis of their hapticity. Different haptoligands have different reactivity and they will form different kind of compounds with the different stability and structural features. We are entering into some important organometallic compounds of D as well as F block elements. First of all, we are discussing sea salt, and this sea salt with the molecular formula KPtCl3 eta 2 CS2 double bond CS2. That is, in ethylene the hapticity is 2. That means for the ethylene ligand both the carbon atoms are in the bonding distance from the central metal platinum. And it should be noted that the sea salt is the first organometallic compound that is isolated in the pure form. This is the sea salt is under the name of the inventor W.C. Sees, who is a Danish pharmacist, not a chemist, and discovered the sea salt in 1825. Regarding the structure of sea salt, we can observe that the molecule is a square planar complex. It is prepared by the simple reaction K2PtCl4, that is potassium tetrachloroplatinate 2. On reaction with ethyl alcohol, we will get a sea salt as its monohydrate. We can see one water is present in the crystal lattice, that is monohydrate, and the liberating side molecule, the liberated molecule is KCl, side product is KCl. And this is the structure. The central coordination complex is said to be square planar in nature, and KPtCl3 minus is Cl3 CH2CS2 minus is inside the square bracket, that is coordination sphere is that negative charge moiety, and K plus is out in the present in the ionization sphere. This is the square planar structure of the sea salt. Now, the pi acid ligand donate electron density to the metal d orbital. This is the structure feature of the bonding feature of the sea salt. The platinum chlorine bond trans to ethylene group is significantly longer than cis platinum Cl bond. In the structure we can see there is a cis as well as a trans position having chlorine atom platinum Cl bond, and this point is about length of the PTCl bond in trans and cis position with respect to ethylene. The CC distance, carbon-carbon distance, is 1.375 angstrom, that is slightly longer than actual value of carbon-carbon double bond distance in ethylene. This clearly indicates that there occurs some back bonding interaction between ligand and the central metal platinum in sea salt. Now, the first sigma bonded organometallic compound. The first sigma bonded organometallic compound ever reported is diethyl zinc, and this diethyl zinc is otherwise called the Franklin reagent. The Franklin reagent, the name is under the name of its inventor, Edward Franklin. Yes, the reaction for the synthesis of diethyl zinc is shown here. 3 molecules of ethyl iodide reaction with the 3 molecules of zinc, we will get Et2Zn, diethyl zinc, C2H5 zinc iodide, and zinc iodide is also liberated as the side product. This is the Bolansky model structural representation of the first sigma bonded organometallic compound diethyl zinc. Now, another category of organometallic compounds, that is nothing but metallocins. Metallocins, whenever we are hearing about the metallocins, we came to know about sandwich compounds, and we can enter into details of the sandwich compound later. A metallocin is a compound consisting of 2 cyclopentadienyl anions bound to a metal center. That metal center is preferably in oxidation state of +3, resulting in the general formula C5H5 twice M. This C5H5 twice M can be simply denoted as Cp2M. Since both the Cp rings, both the cyclopentadienyl anion rings contain 5 carbon atom, and all such carbon atoms are in the bonding distance from the central metal, the hapticity of Cp ring in a metallocin is equal to 5. Hence, we can denote it as eta 5 Cp twice M for every metallocin. This represents the general structure of a metallocin. There are so many examples. We can replace metal with the metal 2 plus ions from the 3D series or 4D series. There are several such metallocins, and we can go through that. For instance, if we are dealing with the 3D series moving from scandium to zinc, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper, zinc are the 10 elements of the 3D series. Out of that 10 elements, 6 elements form metallocin, more or less stable metallocins. They include the first member vanadocin, second one chromocin, manganocin, ferrocin, cobaltocin, and nickelocin. Among these 6 members, 6 metallocins of the 3D series, the most stable and most thoroughly characterized one is the ferrocin molecule, that is eta 5 Cp twice Fe. It is a compound of iron. That is an important compound. Its structure, reactivity, complete chemical reactions are totally studied in a very established fashion. Other sandwich compounds, in addition to metallocin, that is metallocins contain Cp ring, and in addition to metallocin, there are several organometallic compounds that exist in the sandwich structure. Some other examples other than metallocin are dibenzene chromium. Here, instead of the Cp ring, 2 benzene rings are in the sandwich form. In the middle position, there is a chromium. So, instead of Cp ring in metallocin, Here we are having 2 benzene rings and the hapticity of the benzene ring is 6. That means all the 6 carbon atoms of each benzene is in the bonding distance from the central metal chromium. This designate another important example for sandwich compound. And sandwich compound may have structural variations also. For instance, bent sandwich compound is also there. For example, tantalum and titanium can form bent sandwich molecules as shown here. The first compound Cp twice tantalum hydrogen 3. 3 hydrogen atoms are ligands. And in the second case, titanium Cp twice 2 Cp rings are there and Cl2. These 2 compounds are good examples for bent sandwich molecules, that is some structural deviation from the normal sandwich structure. Another possible sandwich structure is half sandwich structure, that is provided by vanadium compound as well as chromium compound. The molecular formula can be assessed from the structure. Now, the most important metallocene, ferrocene. Ferrocene is actually bis eta 5 cyclopentadienyl iron 2, denoted as molecular formula Fe eta 5 Cp twice. It occurs highly stable orange crystal with a melting point of 174 degrees Celsius. In solid state at low temperature, the rings are in staggered arrangement. However, at very low temperature, the rings are in eclipsed arrangement. Imagine my first palm as the first Cp ring, second palm as the second Cp ring. If they are arranging like this and at the middle position there is iron, this arrangement designates eclipsed arrangement. But this eclipsed arrangement is present at very low temperature, less than 110 Kelvin. At ordinary condition, it to form a staggered arrangement like this. The staggered and eclipsed arrangement is depicted here. The preparation of ferrocene is from CPD, cyclopentadiene. On reaction with potassium hydroxide, we will get CPD anion. Further reaction with the ferrous chloride produces ferrocene. There are so many methods for the preparation of ferrocene also. Metal carbonyls are another important category of organometallic compounds. Metal complexes in which carbon monoxide acts as a ligand are called metal carbonyls. The history of metal carbonyl came from Ludwig Mond. He introduced a process called Mond's process for the purification of nickel. In the metallurgy of nickel, impure nickel is purified by using a chemical process called Mond's process. In that process, impure nickel is treated with the carbon monoxide to get nickel tetracarbonyl. On further decomposition of nickel tetracarbonyl produces pure nickel, and in that reaction there occur the formation of the first metal carbonyl, that is NiCO4 times. NiCO4 times is pictorially shown here. There are so many mononuclear carbonyls. What is a mononuclear carbonyl? The metal carbonyls which contain one metal atom per molecule. Per molecule is known as mononuclear metal carbonyl. There are so many examples. Some simple examples are tetracarbonyl nickel, NiCO4 times, shown by the first structure. Second one, iron pentacarbonyl, designated by the second structure, and CrCO6 times, that is chromium hexacarbonyl. And all these carbonyls contain only one metal center per molecule. Hence, they belongs to the category mononuclear carbonyls. Moving on to another category, that is binuclear carbonyl. What is a binuclear carbonyl? By definition, a binuclear carbonyl consists of 2 metal atom per molecule. For instance, CO2-CO8. CO2-CO8 in solution consists of no bridging carbon monoxide ligand. However, in the solid state, 2 carbon monoxide also bridges the 2 cobalt centers. That is the structural feature of cobalt octacarbonyl in solid state and in solution phase. Some other examples also there for the binuclear or dinuclear carbonyl Fe2CO9, then M2CO10, where M is equal to molybdenum, technetium, rhenium provide another examples for binuclear or dinuclear carbonyls. Now, polynuclear carbonyls. What are polynuclear carbonyls? With increase in number of metal, if there is more than 2 metal centers per carbonyl, we can designate it as a polynuclear carbonyl. Some examples are Fe3CO12. Clearly, it is trinuclear carbonyl. Another example, M3CO12, where M is equal to ruthenium or osmium, provide trinuclear carbonyl examples. Then tetranuclear carbonyl IR4CO12, that is iridium carbonyl, is another example for polynuclear carbonyl. With increase in number of metal centers, we will get higher and higher structurally variant polynuclear carbonyls. Now, we are going to assessing the stability of a carbonyl or an organometallic compound. For example, if we are getting the molecular formula of some organometallic compounds, the rule at the thumb that help us to assess its stability came from EAN rule. This is the first simplest rule to assess the stability of an organometallic compound or simply a coordination complex, that is the effective atomic number rule. We can enter into the details. The sum of the electrons on the central metal atom and the electrons donated by the ligands in a complex or an organometallic compound is called effective atomic number. That is, effective atomic number is the total number of electrons from the central metal and that donated by the ligand. In organometallics, the ligand may be a carbon containing moiety like a carbon monoxide, like a CP ring, etc., etc. This rule can also be applicable to coordination complex, a simple coordination complex, where the ligand donate electrons to the central metal. So, this EAN rule is not limited to organometallic compounds or carbonyls, it is applicable to every coordination complex also. Now, the EAN rule states that the EAN must be equal to atomic number of the next nearby noble gas, next incoming noble gas. We can illustrate this by using several examples. For instance, we can apply the effective atomic number rule to assess stability. For instance, titanium hexacarbonyl, vanadium hexacarbonyl, vanadium hexacarbonyl with negative charge. The last group is called the carbonylate anion. How is it possible to evaluate, to find out the effective atomic number rule for this molecule and to assess the stability based on EAN rule? For example, first I can take the molecule titanium hexacarbonyl and first of all we have to compute the EAN value, the effective atomic number value. What is effective atomic number? The total number of electrons donated by the ligand plus that from the central metal. Here titanium is the central metal. Number of electrons present in titanium, that is equal to its atomic number. Scandium, titanium. Titanium has atomic number 22. Then there are 6 carbon monoxide ligands. 6 carbon monoxide ligands. Carbon monoxide is a monodentate ligand. It can provide 2 electrons. So, each carbon monoxide donate 2 electrons. Hence, here we are having a total of 6 carbon monoxide ligands. Hence, 6 into 2 electrons. That is, we are having a number of 12. So, effective atomic number will be equal to 22 electrons from titanium and 12 electrons from the ligands, that is equal to 34. And as per the EAN rule, it should be noted that EAN must be equal to atomic number of the nearest noble gas. The nearest noble gas in this range is having atomic number 36, that is krypton. And here we are having En is equal to 34 only. And atomic number of nearest noble gas is 36. So, as per the En rule, TiCO6 times is not stable. We can enter into other example, vanadium hexacarbonyl. Vanadium is having atomic number 23. Here also 12 electrons from carbon monoxide ligand and En is equal to 35. Again 1 electron is short to attain the stable configuration. And finally we can take vanadium hexacarbonyl with a negative charge. Here vanadium provide the same 23 electron. 6 carbon monoxide ligands will provide 6 into 2, that is equal to 12 electron. And you can see the presence of a negative charge here. The negative charge will provide one more extra electron, and that one extra electron, total number of electrons here, En is equal to 36, which exactly match with atomic number of the nearest noble gas, that is krypton. So, among these three moieties, the most stable one as per the EAN rule is vanadium hexacarbonyl minus, that is a carbonylate anion of vanadium. This is also possible to apply further complexes. Nickel tetracarbonyl, nickel with atomic number 28 plus there are 8 carbon monoxide ligand, 8 electrons from carbon monoxide ligand. This is 36. This is stable as per the EAN rule. Next case, FeCN 6 times 4 minus. We know that iron is present as iron 2 plus. Iron 2 plus. Iron is having atomic number 26, but iron 2 plus is having 24 electrons. And there are 6 ligands, 6 cyanide ligands. Each cyanide ligand will provide 2 electrons. So, 6 into 2, that is equal to 12. Here there is a total of 36 electron, which is again stabilized by the EAN rule. And the last compound, FeCN 6 times 3 minus, or simply the ferricyanide ion. The ferricyanide ion is unstable as per EAN rule. What is the reason? Here iron is present as iron 3 plus. For iron 3 plus, the total number of electron is only 23, and 6 cyanide ligand will provide 12 electrons, and we are having a total of 35 electron only. So, this is unstable as per EAN rule. Thus, by computing the EAN and comparing it with atomic number of the nearest noble gas, we can assess the stability of the organometallic compound as well as simple coordination compounds. The 18 electron rule, this one is a more refined and advanced version of the EAN rule. And according to 18 electron rule, when the central metal ion or atom in a complex compound acquires noble gas electronic configuration n-1 d10 ns2 np6, there will be a total of 18 electrons. See, this 10 electrons, 2 electrons here and 6 electrons, having a total of 18. So, whenever the central metal atom or ion acquires 18 electron arrangement by this configuration, the complex or organometallic will be highly stable. If a compound is stable by 18 electron rule, definitely it obey the EAN rule also, because 18 electron rule is the refined version of EAN rule. There are so many methods for electron counting. The most popular method is called neutral atom count. Here we are taking the electrons from the central metal, preferably the electrons from metal n-1 d subshell, ns and nb orbitals, and we have to add electrons from the ligand, and in the neutral atom count we consider ligand as neutral moieties. Based on this neutral atom count, we can find out the molecule is obeying EAN rule or not. A simplest example is iron pentacarbonyl. In iron pentacarbonyl, iron is having the configuration 3d6 4s2. So, 8 electrons in iron itself, and each carbon monoxide provide 2 electron and 5 into 2 10, and this iron pentacarbonyl simply obey the 8 electron rule and it is a stable species. In a similar argument, it is possible to say that NiCO4 times will also obey 8 electron rule. For example, nickel is having the configuration 3d8 to 4s2 and total 10 electrons from nickel, and 4 carbon monoxide ligands are there, it will provide 8 electron and the total number of electron is 18. In ferrous cyanide ion, here also we can count it is an 18 electron species, but from FeCN 6 times 3 minus, as per the neutral atom count, there will be only 17 electron, and that is 1 electron shortage to attain a stable structure or stable configuration. So that molecule is unstable as per the 18 electron rule. And Mn2CO10 is a molecule where we can see the presence of a metal-metal bond, and here there are 2 metal centers, and we require a total of 36 electron. Per manganese 18 electron is needed. For 2 manganese there are 36 electron must be there, but on counting we will get only 34. 20 electrons from 10 carbon monoxide and 14 electrons from each manganese. That is, there exists a shortage of 2 electrons, but that is already compensated in the structure, because in Mn2CO10 there exists a manganese-manganese bond. Manganese-manganese bond is also there. All these are carbon monoxide, and this manganese-manganese bond account 2 electrons. Therefore, 34 plus 2, 36, 36 for 2 manganese, and per manganese the configuration will be 18, and this one is also stable based on 8 electron rule. Ferrocin, eta 5 Cp twice Fe, this is ferrocin. Okay. This molecule, iron is having 8 electron, each Cp ring will provide 5 electron, 2 Cp rings are there, so there is a total of 18 electron, that is also stable as per the 18 electron rule. Now, there are so many complexes of lanthanides and actinides are there. These are some important lanthanide organometallic compounds, several structural variations are there. This also form organometallic compounds of lanthanide, eta 8 C8, H8 twice cerium is a good example, and so many organometallic compounds from actinides also. The most popular example is uranosin. It is not a metallosin. Metallosin contains Cp ring, but uranosin contains cyclooctatetraenyl ion as the ring structure. And this is the method of preparation of uranosin. So many examples from actinide series also, and that all about the presentation on organometallic compounds of D and F block elements. Thank you all.